is what allowed us to discover the presence of new particles, which I'm going to show you why we think these new particles exist. But just to give a little teaser for some other talks you're going to see, given all of the rich structure happening here in the standard model, this whole Venn diagram with all these different particles and forces, I think it's not too inconceivable that the dark matter also has its own kind of interesting structure. So perhaps, you know, there's its own bubble in the Venn diagram, which maybe talks directly to the particles that we know about and has some degree of overlap between these different Venn diagrams. It's also possible that maybe there's no direct overlap, but it's really great we still have gravity and we can still learn about what's going on inside of this new bubble of the Venn diagram. So gravity is really, really powerful in this sense. So with that kind of as the motivation, I want to now walk you through different pieces of evidence for dark matter gravitationally. Can we actually see dark matter over a wide range of systems? And I'm going to briefly give you a little tour through all of these systems. These systems span about 9 orders of magnitude in length and about 17 orders of magnitude in cosmic time. So from the very, very early baby universe all the way to the present day, we see the fingerprints of dark matter across space and across time. Okay, and this is something where we can, again, this is a science question. We can actually see how these systems look in nature and empirically sort of drive the questions that are motivating us to think more about dark matter. So that's what we're doing, and I'm going to just give you a brief tour of a bunch of these systems, starting pretty locally, so talking about local evidence for dark matter in galaxies like the Milky Way. And this is a very famous example. This is called a rotation curve, and it tells you how fast things are rotating as you go farther and farther away from the center of a galaxy. Okay, and so now here in this image, we have this really bright galaxy. Given how bright it is, we kind of expect that most of the stuff is going to be at the center of the galaxy. And as we know, as you get farther and farther away from something that's massive, the speed of how you rotate around that thing is going to have to go down. Okay, so you don't need to go as fast to orbit. And so we would expect, given where the stuff is, that as you go out to larger and larger radii, the speed is going to drop. But very famously in the 70s, Vera Rubin actually performed this measurement using both starlight as well as neutral gas, which faintly emits radio waves with a length of 21 centimeters. What happened there? And what she found was that actually the speed doesn't drop off with radius. It actually stays more or less constant. And you actually need additional matter to explain this observation. So the stuff that's going so fast out on the outskirts of the galaxy, if there wasn't additional matter kind of binding things together and pulling it in, that stuff would just fly out of the galaxy and we wouldn't see it anymore. So it would be going too fast to stay bound to us. So the fact that there's stuff out there moving at that speed that we can observe must mean there's some additional matter holding things together. And since those days, since the days of Vera Rubin, we've gotten really, really good at doing this, and we've seen this kind of pattern in a bunch of different galaxies. But it's actually a much richer story than that, because when we look at other galaxies, it turns out there's a wide variety of different kinds of galaxies out there. In some cases, we see galaxies where the dark matter is actually the vast, vast majority of the mass of the entire galaxy. So this is a dwarf galaxy called Eridanus 2. Okay, it's the sort of thing where you can barely tell there's even a galaxy here. It's so extremely faint. Okay, but dynamically you can measure how fast are the stars going, and you can figure out how much mass there is in this system. And you can see that there's actually a lot of mass there. It's just that you can't really see it. Okay, there's another example. So this is a very, very dark matter dominated example, but you also have examples where there are galaxies that have almost no dark matter in them whatsoever. And this is an example called Dragonfly 2. It's a galaxy, again, it's very, very diffuse. You can actually see background galaxies behind it that are kind of shining through it, almost as if it's like transparent. So it's a very, very diffuse galaxy. It's as big as the Milky Way, but it seems to be much, much less massive, and it seems to have almost no dark matter in it. Okay, so what this picture, these different pictures teach us is that we can think of dark matter as being kind of like an ingredient. Okay, so I actually really like to bake, and so it's like if you have your cookie recipe, right? You take more flour and you add some milk, and now suddenly you have a cake recipe. Okay, and the same is true with galaxies. You can make different galaxies out of different types of ingredients. Okay, so that's kind of what we see. We see a really big diversity of different kinds of galaxies out there with a different mix of dark matter and regular matter. And so this is something that cannot be explained if you just, let's say you try to fix the theory of gravity. You can't explain all of this great diversity. You really need the freedom of adding different ingredients to make a different recipe. Okay. We also see evidence for dark matter in clusters of galaxies. So not even just in the galaxies themselves, but when they cluster together. And here's a very famous example. It's called the bullet cluster. So it's an example of two galaxy clusters that have undergone a merger. And we're actually looking at the aftermaths. So there's a lot going on in this image. So I want to break it down for you step by step. So you're seeing a bunch of things. So first of all, you can point the Chandra X-ray Space Telescope at this region of the sky. It's able to pick up all the X-rays coming from that region. Okay, and that's what's being shown here in pink. Okay. So now what's happened here is that these two galaxy clusters have ripped through each other very, very fast, roughly 1% of the speed of light. So fast that it was a supersonic merger. Okay, so when you look at these pink regions, particularly the one on the right, you might recognize that as being a bow shock. So that's similar to the shock wave that happens when an airplane goes above the speed of sound, above Mach 1. So that's what's happened here. As these two clusters have ripped through each other, you've created this big shock wave. Another thing that's happened is that as these two galaxy clusters have merged through, you have all this drag, you have all this viscosity going on, which can convert the bulk motion of the merger into thermal motion. And so this stuff is thermally emitting X-rays. Okay, it's extremely, extremely hot. It is thermally emitting X-rays, and we're able to pick those up with Chandra. And so from this image, we can tell where the regular matter is. At the same time, we have these blue regions. That's the mass that we infer using gravitational lensing, which is this really, really cool technique. So Einstein taught us that mass can bend space and time, and in doing so, it can deflect the rays of light. And it's just like when you have a pair of glasses where you can deflect rays of light, utilizing the fact that you have a different speed of light inside of glass as opposed to air. The same kind of thing happens here. You have a curvature of space-time which bends the light and can either focus it, defocus it. You can warp your images, same way with a pair of glasses. And so if we can see examples of this lensing, we can actually try to reconstruct what was the mass doing the lensing. What did the glasses look like? What prescription did we have? Okay. So here are a couple of examples. Like here's a really famous example. It's called an Einstein ring. This is an example of a strong lensing event. You can also get kind of fun examples like this where the universe seems to be smiling at us. Okay, so lots of fun examples. And when you go back to this image, it turns out we see lensing in this image. So the background galaxies are being lensed by the two clusters that have merged through each other. And from reconstructing what the prescription of the glasses was of the universe, we can say that the lenses had to be in those blue regions. And crucially, these two regions are not sitting on top of each other. They are spatially separated from each other. So why did that happen? Here's an artist's conception of the bullet cluster. So here's what it would have looked like before the merger happened. So the pink regions and the blue regions are sitting on top of each other. They're both part of the same cluster. But as the merger happens, so they rip through each other, okay? And what starts to happen is that the two clouds of pink stuff, the ordinary matter, it starts to exert a viscosity, a drag, okay? The two clumps exert a drag force on each other, which means that the pink regions, the regular matter, it slows down. But the blue regions don't slow down. They just keep going and are not slowed down. And so over time, you pick up a separation between the two because they have different speeds. So the pink matter, the regular matter, which we know it has viscosity, right? It's slowed down. The blue stuff, whatever is making up that stuff, it has to gravitate like matter, but it does not feel this kind of viscosity or this kind of drag force. It's very inert. It's not interacting at all. So that's another piece of evidence for some kind of matter. And now we're really seeing for the first time evidence that this stuff really can't be behaving in the same way as ordinary matter. It has to have completely different properties as ordinary matter. So I want to now talk about the universe on the largest scales. I promised you all these orders of magnitude, so now I want to go to the largest possible scales. And I want to tell you about this really cool thing called the cosmic microwave background. So stick with me for a moment. I promise it'll be really cool. So the speed of light is finite, right? So it takes time for light to go from point A to point B. And that means when I look out at you, the audience, light travels around a foot per nanosecond. So you're several feet away. So I'm seeing the audience, how you guys look, several nanoseconds ago in time. There's a time delay between when the light was bouncing off of your faces and when it's hitting my eye. Now, if I take this idea and I apply it sort of iteratively out farther and farther, okay, if I look at a distant star, yeah, I'm not seeing how that star looks right now. I'm seeing how it looked many, many years ago. When I look at galaxies, I'm seeing how those galaxies looked potentially millions to billions of years ago. And I can just take this idea and keep repeating it further and further to the point where I get out to the distant reaches of the universe, and I'm looking as far back in time as I can possibly go. And I can take this to the limit, try to get as close as I possibly can to the time of the Big Bang, but something's going to stop me from doing that. Something's going to prevent me from looking at the Big Bang. And what that is it's the CMB. So when I'm looking back in time, because the universe is expanding, when I look back in time, that's a time when the universe had to be smaller than it is now, right? So if I play the movie in reverse, it's not expanding, it's contracting, okay? So when the universe was smaller, it had to also be a little bit hotter, okay? So if you just keep squishing stuff together, it's gonna get hotter and hotter and hotter. That's like the ideal gas law. If you ever tried like pumping air into your bike tire, you've maybe experienced this, your bike tire gets really, really hot. So eventually you bring all this stuff together and it gets so hot that you can't form neutral atoms. You have not a gas, but you have a plasma. Okay, so the thermal energy of the universe is able to rip electrons off of protons. Okay, there's so much thermal energy in this very, very dense region of space now. And plasmas are not transparent. Plasmas are opaque to light because the light actually is able to scatter off of all of these free electrons, which are represented as white dots in this cartoon. So the light is scattering all the time inside of this plasma. Okay, so that's why you can't see past a certain time, right? Because when you look at the earliest times, eventually you hit a point where you hit this plasma screen and you cannot see inside of what's going on there. Okay, that's the surface of glass scattering. And you might think, okay, well, then there's nothing we can learn about what's happening at these early times. We can't see inside of this plasma. It's opaque, so we can't figure out the physics. But it's actually a lot like the physics of weather. Right? Because when we look at a cloud, it's the same thing. We can't see inside of a cloud because clouds are opaque, but we can actually look at what the surface of the cloud looks like, and we can use that to infer something about what the weather is going to be. And the same is true here. So when we study this surface of glass scattering, this is actually what we see. Okay, so when we look out into the distant reaches, we see the cosmic microwave background, we see this plasma screen, okay, and it has these really, really distinct ripples in them, okay? And these ripples are not random, okay? They actually have a really, really rich structure to them. And when you study what they look like, they turn out to have a pattern that implies that there's some sort of fluctuations going on that are behaving a lot like a sound wave. So what could be driving this sound wave? It turns out if you have any stuff in the early universe, any extra little bit of matter, more matter at point A than at point B, then stuff's going to preferentially be attracted to point A. Things are going to want to go where there's more matter because there's more gravitational attraction to stuff where there's more matter. So gravity tries to bring things together to these little special points that have a little bit more stuff. Gravity tries to bring things together, but in this plasma, you can't really cluster stuff together. You can't clump it together because there's really strong pressure pushing back, okay? So this is a fluid. It's like pushing on all of the stuff trying to come together. So what you end up with is competition between compression from gravity and rarefaction because of the pressure inside of this plasma. And those are the two ingredients that you need for a sound wave. You need fluctuations in the pressure because of compression and rarefaction. And so the regular matter is experiencing this pressure. But if you have some component of matter, dark matter, that does not experience this kind of pressure due to this plasma, what happens is that this dark matter just sinks down to the bottom of the gravitational potential. Okay? It's able to just cluster and gravitationally get more and more compact over time without being puffed up by pressure. So what that then does is it means that the regular matter, it feels the fact that there's dark matter there, because now there's this additional stuff causing a gravitational compression. Okay, so if there's no dark matter, the sound waves look very, very different from if there's dark matter, because dark matter is enhancing gravity and it's enhancing the compression. And so we can study these sound waves, okay? Let's say you have a little bit of interaction between dark matter and regular matter. You're going to have very, very different looking sound waves because now the pressure can push some of the dark matter out. Okay, so it's going to change the shape of the potential. It's going to change the amount of gravity that dark matter feels.
You can just press cancel.
There's no mouse here. Hey, we're back. All right, sorry to keep you in suspense like that. As I was saying, so if you have no dark matter, or if you have some weird, properties of dark matter where maybe it interacts a little bit with the regular matter, and maybe it feels this pressure, you're going to change the intrinsic nature of those sound waves. You're going to change the pattern of the sound waves. So here's an example, actually, from my work. So here's a situation where we were looking to test a model of dark matter where it's born out of this plasma in the early universe. And in this model, the dark matter has a fractional charge. The electron is the smallest smallest quantum of charge that we know about in the standard model. And if the dark matter had a charge that was 10 to the minus 10 of that electron charge, this is what the sound waves would look like. So the sound waves would look totally, totally different. And this is a really, really exquisitely precise test. So you can test things at the part per billion or even less than that level of dark matter. And you can really differentiate between dark matter and other things. So this is an extremely, extremely powerful test. And this actually tells us exactly how much dark matter there is. Now, these sound waves then, we're not done with the sound waves. Okay, so you see them in the cosmic microwave background, this plasma screen of the distant reaches of the universe. But then these sound waves actually set the initial conditions of the early universe, which then is what allows you to form galaxies at later times. So you have these little sound waves where you have some regions that are more dense than other regions because of the waves. And so in those more dense regions, you're going to have more stuff there. And so you're going to be more likely to form a galaxy. And so when we compare observations of where galaxies form compared to simulations with dark matter, we can actually compare the two statistically, and the statistics of these two pictures are identical. So we're able to actually say that yes, we think dark matter actually, not only do we see evidence for it, but it played a crucial role in us being here. Because to have the galaxies that we see today, and to have them have all the properties that we see today, you needed actually to have dark matter setting these initial conditions. So we might not be here if it wasn't for dark matter. So I've now given you all this evidence for matter. I have not yet, I think, established that there has to be a new particle. Okay, so I want to actually do a really quick case study. And I want to tell you guys really quickly about the case of the neutrino. That was actually, as you'll see, I'll get to the punchline, that was one of the first proposed candidates for the dark matter. So what is a neutrino, first of all? So a neutrino is just a light little particle, okay? And it was first proposed by Wolfgang Pauli, because what was observed at the time was that when you had beta decay occurring in atomic nuclei, it seemed like the outcoming electron and proton out of the beta decay didn't seem like energy was being conserved. Okay, so you had less energy in the final state than what you had in the initial state. And we know that energy is conserved. That's a law of physics. And so rather than say, well, maybe something's broken about this law of physics, what Pauli did was he added this new particle, the neutrino, which comes into the interaction and it takes up some of the momentum and the energy, and it makes it so that everything is conserved again. And when he did this, he said, I have done a terrible thing. I have postulated a particle that cannot be detected. And in fact, he promised a case of champagne to anyone who could possibly detect this particle. It seemed impossible. Okay, but it turned out he just had to wait a few decades. So decades after he postulated the existence of this particle, it was actually discovered for the first time in the 50s by Rines and Cowan using reactor neutrinos. And then a decade later, it was first detected from astrophysical sources of neutrinos. So he kept good on his word. He sent them a case of champagne because he thought it couldn't be done. And I think there's a lot of parallels to draw with the dark matter story. So we think we understand the laws of gravity, right? We think we understand, we have all these great tests of gravity. We think we understand it. And so, we're not going to throw away the theory of gravity. We're not going to throw away conservation of energy, these laws of physics. Instead, we just have to add some new ingredient. And it might be really, really hard to find. It might take decades, but there's a lot of creativity out there. And so just to come full circle, for the people asking, well, couldn't these be dark matter, right? So you may have noticed that by my own definition of what I mean by invisible, neutrinos are invisible because they don't talk to light, they don't talk to electromagnetism. And so people thought, well, they're dark, okay, and they have an unknown small mass, they could be a dark matter, perhaps. But it turns out the answer is no, because neutrinos have a very, very low mass, okay? So if we know the temperature of the universe, we know the neutrino's mass, we can figure out how fast it's going. And if it's going really fast because it's light, it's not going to clump as well gravitationally, right? If you try to bring everything together due to gravity, if it's going too fast, it's just going to escape. So the escape velocity of the stuff that you try to bring together is very, very sensitive. So the stuff can't cluster, and then you're not going to form galaxies as we know that. So here are two simulations. One of them has cold, non-neutrino dark matter. The other one has neutrinos as 20% of the dark matter. And you can see that these two simulations look very, very different. The neutrino case looks a lot more fuzzy, okay? And the cold dark matter case, the case where it's not neutrinos, you can see that there's a lot bigger structures. The peaks look peakier, the troughs look troughier. Okay, there's a lot more, it's a lot more extreme and it's less washed out. It's more crisp. Okay, so there's a very big difference in the structure that we see if neutrinos are dark matter. And so now we actually know that neutrinos are about 1% of the dark matter. But the 99% of the rest of it, it really has to be something totally unique and different. So the upshot of my talk has been that there's evidence for a new type of matter on a very, very wide range of scales. Okay, and so we can confidently infer that it's there. We know it doesn't behave like regular matter, but we're trying to understand it better. And we have a whole wealth of different astronomical systems where we know that this dark matter is there. And so we can try to use those same systems to learn about what it's doing. And this means there's a lot of room for creativity. So with that, I will wrap up and hand it over to Dr. Saniya Heeba to tell us more about theories about dark matter.
Great. Good evening, everyone. My name is Saniya. I'm a research fellow at the McGill Space Institute. I also work on dark matter, and I'm going to be picking up where Katelin left off and talk to you more about some of the things that we as particle physicists do when we start to think about dark matter, right? So we have all of these observations, we know that it's there, but somehow need to come up with a theory that not only models what we see, but also gives us testable predictions of how we can probe dark matter. And so the experimental part of it, Dave's going to cover after me. So I'm just going to be talking about kind of the model motivations of various kinds of dark matter theories. And I've titled my talk "What's Hiding in the Dark." But if you've been paying attention to Katelin's talk, you know that dark matter is not really dark; it's more invisible. So I think a more accurate title would be "What's Hiding in Plain Sight," and that's what dark matter is. And since it's kind of Halloween season, it's spooky. I kind of went all in and made my talk full of monsters. So you're not going to be seeing any actual particles, but it's going to be artistic representations of various kinds of monsters that dark matter can be. Right, so we're going to be a little bit creative in this science talk. Okay, so just to recap things we learned from Katelin about what we know about dark matter. So completely coincidentally, I think I was also thinking about dark matter when I made that cartoon. Kind of looks like him. But yeah, so things we know. We know that it exists. We know that it's there. We also know to a very good degree how much of it there is. So if you can think about it in terms of the standard particles that we know and love, so in terms of protons, so you can think about it for every proton, you have about 5 or 6 dark matter particles. So in terms of, if you don't want to think about it in terms of particles, you can think about it in terms of just the matter density. So if for 100% matter density of the universe, 20% is the things that we can interact with, so like cats and ice cream. The 80% is whatever this dark matter stuff is. So it's quite a lot of it there in the universe. We know that it's massive, also from Katelin's talk. We know that because it interacts gravitationally, we know that it has to have some sort of mass. We also know that it interacts weakly. So we're sure it interacts gravitationally. We're not sure if there are other interactions. But if there are, because dark matter is invisible, it has to have interactions that are quote unquote weak. And we're going to discuss more about what we exactly mean when we say weak interactions as we go through the talk. Right. So this is once again the plot from Katelin's talk as well, which actually was stolen. But I think it's a very good kind of conceptualization of when you think about dark matter, where do you want to put dark matter on the spot, right? So we know that it definitely exists somewhere outside, so it's only interacting gravitationally. But we can kind of move this blob around and think about particle theory motivations of putting this blob in various places on this graph, right? So, right. So we're gonna, right. So at first sight, this kind of looks complicated because we know that we have these 4 forces in the standard model, and we know we have all of these particles. So you might feel a bit daunted by, proposing a new particle and trying to figure out all possible ways that it can interact, and then what kind of things that would mean for the history of that particle. But it turns out that you can actually do this quite systematically. And in this talk, we're going to be talking about 2 ways that we could do this. And these 2 ways kind of bookend the dark matter origin story in some sense. But yeah, I'm getting ahead of myself. Right. So in the simplest of terms, if you want to define a new particle in the context of dark matter, these are 2 things that you need to do. You need to figure out what the mass of the new particle is. You know the dark matter is massive, so you need to figure out what the mass is. And you need to figure out what the interaction strength of that particle is with the standard model. So we know that it kind of interacts weakly, whatever that means. But you can have a scale of weakly interacting particles. You can have particles that interact weakly. You can have particles that interact weaker than weakly, essentially, right? But slightly more than gravity, maybe. So these are 2 things that you have to kind of figure out when you start writing your model of dark matter. So we're going to start now with kind of candidates of dark matter that people look at in this context, considering only these 2 kind of parameters that we introduced to come up with your theory. Right, and both of these parameters kind of talk to each other, and depending on them, you can write down the origin story of dark matter. And by origin story, I just mean one of the things that we know about dark matter specifically is we know exactly how much of it there is. And that's a very important number. So whatever model of dark matter you write down, the first thing you need to ask yourself is, can I explain this number? Can I explain that 80% of my universe is dark matter, considering this model that I've written down? And so that entire story depends on what we choose for the mass and interaction strength of dark matter. So now we're going to start looking at candidates, and we're going to start with the first one, which is called a WIM. It stands for weakly interacting massive particle. Very creative names. Right, and you can already tell by what it stands for about the 2 properties that we talked about. You can say that it's weakly interacting, so the name, and it's massive. Okay, so it kind of agrees to both of the criteria that we talked about. But then we want to kind of be a bit more quantitative about these 2 things. So what do we mean when we say weakly interacting? What do we mean when we say massive? So for the first part, we're going to look back at this plot again and say, well, we have this force in the standard model that is kind of the weakest force except gravity, and it's called the weak force. So we're going to say that dark matter is a particle that also interacts with this weak force. We're just going to put one new particle in that part of the Venn diagram. And we're going to ask ourselves, okay, if this is true, if dark matter interacts by this force, how do we produce it in the early universe? And it's kind of actually, it's kind of neat how this works out in the end. So as Katelin mentioned, in the early universe, all of the particles are part of like a plasma. And that's because all of them are talking to each other, interacting with each other, scattering off of each other. So in the early universe, you have kind of a particle soup, where all of the particles are kind of chilling out, hanging together. And if dark matter is also interacting with a weak force, it's interacting at the same scale as these particles are interacting with each other. So it's also a part of that plasma. So you start off with a universe that is full of all of these dark particles, all of these standard model particles. And now we need to get to a place where the universe is 80% dark matter and 20% standard model particles. And the way you do that is through annihilations. So we start off with the density of these dark matter particles in the early universe. And because they interact with each other and also with the standard model, you can basically annihilate them and pop out, for example, an electron-positron pair. And then you can do that again. You annihilate two particles, pop out two more electron-positrons. And you can continue repeating this process. Now, if nothing else was happening, but this is all you had a plasma where particles can interact and annihilate, and dark matter, all of your dark matter would just completely be annihilated away into electrons and positrons, and you would end up with nothing. But we do end up with some dark matter, right? And that's the neat part, because there's a key ingredient that's missing on these slides, and it's the fact that the universe is actually expanding. So these annihilations are taking place, but the universe is also growing. So as the universe expands, the two dark matter particles cannot find each other to annihilate. So it takes them longer to do that just because they're spaced out. And so what this does is that it just shuts off these annihilations and it fixes the dark matter abundance. So the fact that the universe is expanding is actually what basically fixes the dark matter abundance once you've fixed its coupling, so its interaction strength and its mass. So this is all nice and cute. The reason that it's interesting and the reason that it's been driving dark matter research for the last couple of decades is because of something called the Wick miracle. And for that, we go back to this slide, right? So now we kind of have dark matter interacting with a weak force. We already know what the weak force is. We know it from the standard model, so we're not introducing anything new or different in that sense. And now I haven't talked about what mass of dark matter there is, but let's just say that it's kind of the same order of magnitude as other particles in our theory. Like let's just imagine the dark matter has the least mass. We know what the least is there. We know it's about 100 GeV or so. So it's like that's like the mass of 100 hydrogen atoms. And we say the dark matter has that mass, right? So we add these two things, and you do the story with the annihilations and the freeze out, like the fixing of the dark matter abundance, and we actually get the correct dark matter abundance that we measure to our experiments. So by introducing kind of very few new parameters and no new scales in our theory, in some sense, we get out the right dark matter abundance, which is why it's called the Wick miracle, and which is why people are looking for ways. And David's going to talk about some of the ways we do that. Right. So this is one part of the dark matter origin story, right? So this is starting from a simple set of assumptions that dark matter interacts with a force that we already know, with a mass that's kind of, justifiable. You end up with the correct dark matter density, and then you also end up with signature, like gentle signatures in your experiments that you can look for. But there is another side to the story, right? So we're still here. We're still, the AstroNight title, how to find dark matter, which means we haven't found dark matter. So if things were just easy, we probably would be having a different conversation. But we haven't seen dark matter, right? So it's an encouragement to us to kind of broaden our horizons a little bit and think about dark matter that interacts with the standard model, even weakly with a weak force, right? And so that brings us to kind of the second part of the origin story that I'm going to talk about, and the dark matter candidate in this case is called a FIT, or a feebly interacting massive particle. We should be in charge of naming everything in the universe. So as the name suggests, now dark matter is feebly interacting. And what this means is, if you look at this Venn diagram again, you have the weak force, gravity, and now we just have another bubble that's kind of a feeble force that's kind of weaker then the weak force, slightly stronger than gravity. And I'm being purposefully vague about this because you can essentially have a whole kind of scale of forces. So you can just tune your interaction strength to be quite weak and still be fine in this kind of dark matter scenario. So this bubble is more like a fog, maybe, or a cloud. It's not really well defined. But anyway, so now we have kind of this new particle that still talks to the standard model, but it talks by a force that is very, very small compared to the weak force, for instance. And now we want to, again, ask ourselves, okay, how do we produce this particle in the early universe? Now, there's one main difference between this kind of origin story and the origin story of the WIMPs that we talked about. And that's essentially this. So with WIMPs, we started out with the fact that because it's interacting by a weak force, it kind of is part of this particle soup in the early universe, right? But now if you have a particle that talks, very little with everything else in the standard model, there's no reason for it to be part of the plasma in the early universe. So you still have a universe that has all of the normal things that we see today. So it has like electrons and quarks and other electrons and neutrinos, but it has no dark matter. So you start off with a universe that is completely devoid of dark matter, and then you ask yourself, okay, I know that right now we have a universe that's 80% dark matter. How do I get to that 80% now? And the nice thing is that you can do everything in complete analogy to the WIMP story. So now you have a plasma that's mostly made of electrons, positrons, quarks, for example, just for reference, I have electrons and positrons here. And you can do that with a similar thing. You can kind of annihilate two of them and produce two dark matter particles. The rate of these processes is going to be small because the coupling between the electrons and dark matter is quite weak, but you can still do that. And we have a lot of time in the universe to do this. So we keep doing this again. We start producing dark matter. Once again, the expansion of the universe is going to shut this process off at some point. And that will give us the density of the dark matter that we observe today. And the reason that kind of physics are interesting is you can think about it as, if you want to think about how to produce dark matter, these can be your two bookends to that story. So you can think about case one with the assumption that dark matter was at some point part of the thermal plasma. And case two, dark matter was not part of the thermal plasma. And then you can build, an abundance of theories that lie somewhere in the middle. And you can do all sorts of crazy stuff with even models that lie in these two kind of origin stories. But it's kind of a nice way to think about how dark matter was produced. Either it was produced by annihilations, or it was produced by annihilations of itself to reduce its density, or it was produced by annihilations of things that we can see that increased its density. So those are kind of the two main origin stories that I'm going to talk about for particles. But then you can also ask, what if dark matter is not a particle? And I think Katelin has given us quite a few evidences saying that we truly believe that dark matter is a particle. And it makes sense as well that it is a particle, because why wouldn't it be, right? But just to make sure that we're covering all of our bases, people do look at non-particle explanations for dark matter. And I'm going to be talking about one of them, because I think everyone would kind of love this. And it's primordial black holes. So we know that black holes exist. We know that black holes are dark. We know that they interact only gravitationally. Then why can't they be dark matter? And so black holes that we know about that are formed from stars cannot be dark matter, because as Katelin explained, we want something that doesn't interact with the plasma for the CMB and everything to work out properly as it does. So we want these black holes to have formed in the very early universe, and that's why they're called primordial. So they form way back in the universe. And then that's kind of their origin story, basically. So in the early universe, you have density fluctuations in your plasma. You can have a region of space where you just have like an overdensity of things, and then that collapses into a black hole. And that's just your dark matter. And they can still, depending on how big these are, they can hang around even present day, and you can figure out kind of the density or kind of the distribution of these particles, of these dark matter candidates today. So so you can have the range of masses. Some of them have been excluded by experiments. So you can just like do for reference. So they can be as small as an asteroid. They can be as big as 13 orders of magnitude, more massive than the sun. And they can be a fraction of dark matter in like all of the range of masses in between these two things. We know that they interact gravitationally, so the ways we detect this would be slightly different to the ways we detect the wind, maybe complementary in that way. So that's the third thing that I wanted to talk about. So we don't really know what's hiding in the dark or what's hiding in plain sight. I've talked about primary black holes, I've talked about FIMS and RIMS. If you want to Google things, you can look up axions, which are another dark matter candidate. You can look up sterile neutrinos, which are another dark matter candidate. But yeah, the thing is that we don't really know what dark matter is, but we have very, very good ideas of what it could be. And yeah, and I think David's going to talk about ways to detect dark matter to kind of bring everything together and figure out, how do we look for these things and find them.
Okay. Well, thank you. My name is David Gallacher. I'm a PhD student here at McGill, and I'm going to tell you a little bit about searching for dark matter, in particular focusing on how do we go about looking for evidence of dark matter right here on Earth. And I'm very fortunate that my colleagues tonight already told you why you should care, why do we think there's dark matter, and what it could be. So they made my job very easy. So I'm going to advance the slides and tell you a little bit about the things we have to think about when we're trying to look for dark matter here on Earth. And I think the first thing you should ask yourself if you're trying to build a dark matter detector is, where is the dark matter? So is it in a particular location? How do we go about looking for dark matter? So if we want to know, if you want to find dark matter, first we have to know where to look. So fortunately, dark matter is everywhere. So as Katelin mentioned, we live in a galaxy, and the galaxy is surrounded by this cloud or halo of dark matter. And as we move through this halo or through the galactic plane, and we're orbiting the center of the galaxy, as we go around the sun, and the sun itself is orbiting the galactic plane, we're actually experiencing the dark matter as you would a wind when you're driving your car or you're riding your bicycle down the road. You feel the wind, the air is standing still, but we're going through it. So the dark matter, because it doesn't interact very strongly, which has been mentioned quite a few times, it will pass, almost all of it will pass completely through the Earth, not really do anything. It doesn't interact very strongly, so it just flows right through us. And we've already seen WIMPs before, so one of the things that we know is that if we were looking for dark matter, and it is a particle, and we can experience this, and we know we're looking for it in the lab, and we have this wind of dark matter going through the Earth, then if we build a detector, we build some sensors that are capable of seeing the dark matter, then we can look for it right here on Earth, which is fortunate. So the next thing we have to ask ourselves is, how exactly are we going to observe this dark matter? If it's very weakly interacting, or it's very rare to see the dark matter, then we have to know what are the possible ways in which it can interact, or in which we can actually observe the dark matter. And fortunately, we have quite a few options. The first thing that we can do is we can wait to see if this dark matter will interact at all with our matter. So this is what we like to call shaking it. So in this diagram, we have a dark matter particle that comes in, interacts with our regular matter, or some atoms in a sensor, some part of our detector, that we're able to observe this interaction. And this is what happens here, is that the dark matter will then continue on its way and just give a little bit of a kick to the regular matter. The other thing we can do, and this has actually been mentioned already, is that we can make dark matter potentially. So if dark matter does have some interactions with regular matter, then it's possible to create it in collisions. So this is similar to what they would do at the Large Hadron Collider. They conduct these sorts of searches, and this is what we call making it, where you smash two regular matter particles together like protons, and you end up maybe potentially sometimes creating something else. and dark matter. And what we look for here is the absence of matter, which would look in our detectors like momentum is not conserved. So we know that conservation of momentum is one of the fundamental laws of physics. So if we have a certain amount of momentum that's well defined going into the system, and then we are only able to observe this standard model particle who's on its way out of the interaction, and we're missing quite a lot of momentum, then that's evidence that we saw something invisible that we weren't able to actually observe in our detectors. Potentially dark matter. The last thing we can do is we can look for signatures of dark matter annihilating itself. So this is what we call breaking it, where you have two dark matter particles that combine together and produce standard model particles. This is kind of like the same thing as before. First, you can end up with lots of different things in the final state. And this can happen somewhere where there's a large gravitational potential, say in the sun or at the center of the galaxy. There can be large gravitational potentials which can increase your density of dark matter and create these annihilations or create favorable conditions for these annihilations. And what we look for is we look for an excess of particles or excess of signal in lots of different parameter spaces where we could be seeing something that's not defined by our already existing theories of how things work. So we're looking, one of the really challenging aspects of dark matter detection research is that you really have to look everywhere because, as been mentioned quite a few times, we don't know what the dark matter mass is, we don't know what kinds of interactions it has. So when we're looking for it, we really just have to measure everything and then see if there's anything that isn't already explained by physics that we know about. And this is a very dangerous thing to do because there's a lot of ways to go wrong. The thing I'm going to talk about the most today and what I'm going to focus on is the approach that has been pursued mostly for the last several decades, and in particular in Canada, which is the shaped approach. So when we have this direct interaction going, the dark matter particles directly interacting and giving some energy, doing something, exchanging some new particle, there is some level of interaction with our standard model particles, which are inside of our detector. So this is what we would call a direct detection of dark matter, and then the other two examples would form indirect detection, where you're inferring the existence of dark matter through its signatures that you can observe. So if these shapes do occur, we have to look for what's going to happen next. And this is really the detector physics kinds of things. We're going to design a detector that is able to observe these types of interactions. We have to know what to do and what we're looking for and what else it could be. So I'll just give you a little comic strip here of what could happen if you had one of these dark matter shapes. So first you would have your dark matter particle come into the detector, and this could be anywhere on Earth, as I mentioned. You get a little kick of energy from the dark matter particle. You do something to the normal matter particle, and I'm being very agnostic about what this type of interaction is. And we usually try to think about things in specific categories, and depending on what kind of dark matter particle you're searching for, or what kinds of detector technology you're using, you'll be sensitive to different types of kicks and what types of interactions are possible. So after we left a little bit of energy in the system, the dark matter particle, as I mentioned, will just continue on its way and keep going. And this particle itself can lose energy in a few different ways. So it can lose energy after it's been given energy. We know that particles like to be, and just things in the universe tend to go down in energy until they're to the ground state. So they have a lower, resting energy. This particle itself will lose energy in a few different ways. So we can lose energy through light. So we can produce light and get rid of energy in that matter. It can produce heat. So it can just get excited and collide with other atoms inside your sensor. And that will result in that change in the temperature, very, very small changes in temperature. Or in other types of signals, the vibrations, etc. Or you can produce charge, so you can have ionization electrons that then we can measure out as a charge or electrical signal from our sensors. And depending on what type of dark matter interaction you're looking for and what types of technologies exist and which signal you're looking for, you can really just pick any combination of these things. And there are some other more exotic searches that I haven't described here, but these are the main ways that people go about looking for dark matter. They'll either pick one or a few of these things and combine them together to try to understand what types of signals they have in their detectors. And afterwards, everything goes back to normal, we carry on, and the sensor is ready to observe more interactions. So mentioned we have quite a few different ways we can go about doing this. And the particulars are dependent on what kind of experiments and what kind of dark matter area you're really looking for. But there's a few problems that are central to all types of searches for dark matter. And that's what I want to talk about next is when you're looking for dark matter, it's really not the dark matter that is the main consideration, it's everything else. So we know that dark matter interactions are very rare, and I like to think maybe dark matter is like looking for a needle in a haystack or a dark matter needle in a haystack. We know these interactions have to be rare. They have to be very weak, so they're not going to interact very strongly in our detector. We're not going to see things very often. And you might ask yourself, okay, well, that's great. This is rare. It's hard to find, but how rare exactly? And unfortunately for us in the detector side of things, is that this is a very large challenge. So it's not like looking for a needle in a haystack, it's more like looking for a needle in several thousand to millions of haystacks. The interactions and the expected rates of dark matter in your detector are very low. So just to give you an idea, just as an example, in a large detector, like the one that I used to work on, which has several metric tons of material that can shake from this dark matter interaction, we expect less than one dark matter interaction in a year. So you have to run your detectors, you have to make them very big. So we have a 3-ton sensor. It takes place, it takes 2 meters of space in diameter in a giant sphere. And we look for many, many years and expecting to see 1 to few over several years. So you may be asking yourself now, okay, well, what is all the hay? Why do we have so much other stuff? And the thing you have to consider is that dark matter isn't the only thing that can shake our sensors. So we build these sensors, we make them very sensitive so we can see these tiny little kicks from dark matter particles. Unfortunately, lots of other things can also do the same thing. So the hay in our analogy represents backgrounds, and like this giant picture, we don't like the hay. We don't like backgrounds. We want to get rid of them, and we want to just focus on seeing these dark matter interactions. The fewer backgrounds that we have, the better we can say that we saw one particle and we weren't fooling ourselves, because as I mentioned before, we're really looking at a broad space, and it's very easy to make a mistake. So one of the main forms of hay that we have is cosmic rays, and cosmic rays themselves are coming from space, so they can come from the sun, they can come from the galactic neighborhood. And these are high energy particles that create showers of secondary particles, which is illustrated in this diagram, where we have a large deposition of energy, blasting apart atoms in the upper atmosphere, creating these showers of secondary and other particles. And these particles will rain down into your lab and into your detector, and they're raining down through us in this lab right now. As we speak, there are many thousands to millions of muons, which are these higher order cousins of the electron. Muons in particular are very damaging for our detector because they move very relativistically. They are fairly long-lived, and they will penetrate very deeply through matter. So they'll pass through the whole atmosphere and continue on. And you can kind of see them in this illustration. The lines that manage to get all the way down to the ground are the muons, and those are the ones that we're really worried about. The other thing that can happen is you can have trace amounts of radioactive elements. So this is because these elements, uranium and thorium in particular, are very long-lived. So the lifetime of these elements is around the same order of magnitude as the lifetime of the universe. So they've been around for a long time. They'll continue being around for a long time. We can't wait for them to decay away in order to run our experiments. We want to look now. So we have to take very special care to make sure that we don't introduce any more radioactive elements into our sensors, because the radioactivity emitted from these elements and from their decay products will cause these shakes in our sensors. So this is really bad. I mean, if we wanted to build a dark matter detector in this room, it basically would not work. At least when we're looking for certain types of interactions, which are similar to the types of things that natural radioactivity and cosmic rays can do. Some forms of some other interaction types are more easily accessible in a normal lab environment, but for our case and purposes, when we're looking for these very weakly interacting massive particles that are quite high in mass, we can't do it here. We have to go somewhere else. So where we like to go, at least here in Canada, what we like to do is we like to go to SNOLAB. In order to shield ourselves from the cosmic rays, we actually build our detectors deep underground. So SNOLAB is Canada's underground research lab, and it is the world's deepest clean facility, located 2 kilometers underground in Sudbury, Ontario. And because it's located so deep underground, we actually get a lot of shielding from these particles, so we reduce our amount of muons that we expect to see in our detector by about a factor of 1 billion. So by going from here to underground at SNOLAB, we're really getting rid of quite a lot of these things that can cause interactions in our detectors, which makes it very hard for us to see the dark matter signals. SNOLAB is actually even better than just being 2 kilometers underground, because Sudbury is located on the Canadian Shield. When you go 2 kilometers under the Canadian Shield, you have quite a large enhancement factor because the shield is so dense. So SNOLAB is really the world's premier facility for doing underground physics. And in the last few minutes, I'm just going to tell you a little bit about what kinds of dark matter detectors and experiments that are located at SNOLAB. So SNOLAB is host to some of the world's leading dark matter experiments. And depending on what types of dark matter regimes they're looking for, what types of interactions they're looking for, these different experiments will look for things in different ways. So I've listed a few examples here, and I encourage you to go through and read their pages if you're interested in learning more about the specifics of how each detector works. But just briefly, in my first example here, which is the G3600, which is my former project, is an example of a sensor that only uses the light signal. So we wait for the dark matter interaction to come into the detector. It will produce some energy. The energy will be deposited in something called a scintillator, and this material will emit light in proportion to the energy left behind. So by measuring how much light we see, then we can make a statement about how much energy and what types of particles cause those interactions. And that's how we go about looking for dark matter with the D3600 detector. NEWS-G is a totally different approach. So NEWS-G is a giant charged sphere. It's about 1 meter in size, and they're looking for dark matter signatures by measuring the electric charge. So dark matter could come in and scatter off one of the electrons that's inside the detector, so it's filled with a gas mixture of a couple of different gases. And if the electron is knocked off the gas, this whole sphere is actually kept under an electric field, and there's a rod in the middle that draws in all charged particles that are emitted. So all these electrons that are emitted from these dark matter interactions and creates a huge avalanche of electric charge. So you take one electron, which may be produced from this dark matter interaction, where it's very weak. We only have a small scatter, produces one ionization electron. So the threshold and how much energy that is required to do that is very small. And then you get a massive amplification process by you can take a single electron and turn it into 1 billion. So that's quite good. That means that we can see a single electron scatter, and we can tell the difference between 1 and 2 and other types of signals that we get. PICO does a totally different thing, and it's a very interesting experiment. So they're mostly focusing on measuring the heat deposited in the detector. So like I mentioned, if this energy is left behind, we get this little shake, these vibrations and the energy that the regular particles will interact with each other, knock into each other, and very, very, very slightly warm up. And PICO looks for heat by keeping their detector in a super heated state, so that even a small change in the temperature of the material inside will cause a phase change inside the detector. So you'll go from this superheated fluid into a gas, and they'll form a bubble, and then they actually just take pictures of the bubbles. Depending on how big and how fast the bubbles grow and how many there are, you can tell how much heat is left in the system, and it is very, very sensitive to these types of searches. So this is just kind of an example of 3 different technologies that look for different types of dark matter using different ways. And I'm sorry to report that we have not found dark matter yet. We have no confirmed direct detections of dark matter that have been made. But as I mentioned, the space of possibilities is large, and the things that we can look for is large. So a lot of the searches in the past several decades have been focused on weakly interacting massive particles. But it's possible that nature just isn't that way. We have much smaller or much more massive dark matter candidates that are the actual that form the dark matter in the universe. And because the space of possibilities is so large, we have to just keep looking in different directions, using new technologies, coming up with new ideas to measure these different types of signals in different combinations, so we can really probe the most sensitive things. So thank you for your attention.
So thank you to our speakers again for those amazing talks. I will invite all three of you to come sit up here because we have our question period. So I will hand the microphone off to the speakers, and also I'll just ask you to please repeat the question so that people on Zoom can, or on Zoom and YouTube can hear.
Stop sharing.
All right, so I'll pass the microphone, and if you have a question, just raise your hand.
To Mr. Gallagher, if you had some kind of detection, how would you know that that's caused by a dark matter black hole, not by something else? For example, extremely energetic neutrino. How would you know?
So this is a great question. So the main thing that we need to do when we're designing a detector, looking for dark matter or any other type of physical signature, is to come up with ways using that detector to measure, to tell the difference between one type of particle interaction and another. And this is, we call this particle identification. It's a fundamental part of the technology. So I really skimmed over the details of every particular detector. So they all do this in different ways, using different parts of the experimental signature. Highly energetic neutrinos is actually one of the hardest examples, and it's one of the things that is the most difficult to tell the difference between a neutrino and a dark matter candidate, because neutrinos also don't really interact. So we saw the quote from Polly before. There was a wager that nobody would ever, the chances of this happening is very unlikely. Now we detect neutrinos all the time. There are neutrino observatories all over the world, but they're massive. So in Snow Lab, there's the SNOW experiment, the eponymous SNOW experiment, which uses thousands of tons of water, so thousands of tons of material in order to see a few neutrinos a year. So these neutrino interactions are also very rare. One thing that we can do with neutrinos in particular is look at the kinematic signature, where because we know where most of the neutrinos are coming from, most of them are coming from the sun or from the atmosphere above us being produced in these showers. Dark matter has a different preferred direction. It's the direction that we're traversing the galactic plane while rotating about it. So we call this, looking towards Cygnus, which happens to be the constellation that's in the same orientation as the dark matter wind that I mentioned. So if you can look at the direction that the nucleus, that the interaction is happening, and what directions those particles will go afterwards, then that's quite a lot of information that people want to use. I will say none of this has been done before, and people are still trying to make these better detectors that are capable of doing this type of differentiation.
So I know that in this presentation you have emphasized heavily that dark matter most probably be a particle, and that one other possibility could be that it might be primary black holes. But is there a reason why we're not considering the fact that maybe our basic assumptions, as to say our theory of gravity, could perhaps be wrong or incomplete, considering the fact that we still do not, we're still incapable of uniting quantum mechanics and general relativity.
Okay, maybe I can say a few things and I can add to it. So the question was, why do we think dark matter is a particle or like black holes and not a modification of gravity? And I think the answer to this might differ depending on whom you ask. So the evidences that we have for dark matter span, as Katelin explained, a range of scales and a range of time steps. And one of the strongest evidences for dark matter that we have is the CMB, and especially like the an isotropy, so this sound wave curve of CMB that we discussed. And it is impossible right now to reproduce that. And so people do look for modified gravity explanations for dark matter, but right now it's impossible to explain the shape of that exact curve, considering just a modification for gravity. Yeah, I don't know if you want to add anything.
Yeah, I can add more to that as well, just because you specifically mentioned like quantum gravity. So the scale where we expect quantum gravity to start to matter is on really, really tiny length scales, whereas we see dark matter on the largest spatial scales of our universe. And that's a scale where we understand gravity really, really well. Like I mentioned, like we have all these like great simulations that match everything that we observe. We just have to add dark matter. So we think actually there's nothing wrong with the theory of gravity. Similarly, like I mentioned before, you have these different kinds of galaxies that, you know, they have the same mass or they have the same spatial size, but they seem to have very, very different ingredients. And so if you have a theory that is a modified theory of gravity, you also can't really explain that, because you would think, well, you know, if I have to modify gravity, right, things that have a similar mass or similar size should have the same kind of gravity. And that's not what we see. We see that we actually need an additional component, an additional ingredient of matter. So yeah, I mean, we have all these great tests of Einstein's relativity. We have all these gravitational lensing things. We have LIGO. We have the observation of M87 star by the Event Horizon Telescope. So we're pretty sure, you know, there's a headline every few years, you know, Einstein was right again. Like we're pretty sure that we have a pretty good understanding of gravity on the relevant astrophysical scales. There still is work to be done to unite it with quantum field theory, but again, that's on very, very tiny length scales, not scales where we know that there's dark matter.
Yeah, so we have dark matter halos like around our galaxy and our solar system, but seeing that dark matter doesn't interact with itself other than like gravity and all that, what's stopping that dark matter from just clumping up into like a really small, dense area like we see with planets and stars and regular matter? Like, why is it a halo kind of like a blob in our solar system and galaxy?
So the question was, if we just have a bunch of dark matter and we know it interacts gravitationally, what's to prevent it from clumping up like the way we see planets and all these other things that clump up in our universe? And the simple answer to that question is because ordinary stuff can cool down. Okay, so if you think about you know, dark matter as orbiting in some kind of big potential, right? So it has to obey conservation of energy, conservation of angular momentum, right? It has to obey those laws. And so if dark matter can't cool down, and if it's on a stable orbit, it's just going to keep doing that same orbit for all of eternity. Regular matter also has to obey those same laws, but regular matter has this additional property where it can cool down. So for example, you know, you can have either like things like synchrotron radiation, cyclotron radiation, Bremsstrahlung radiation, if it's a plasma, or you can have atomic lines where you radiate away radiation because you have an atomic transition. So you have a bunch of ways of like radiating away light, which carries away energy out of the system. So when regular matter cools down by emitting light, what happens is that then now the orbit changes, because now you've lost a little bit of energy, and so now that orbit gets a little bit compressed. And over time, that's how you form these more compressed structures. So when you have you look at the disk of our galaxy, right? The reason why it has that disky shape is because when you lose that energy and you cool down, you still have to conserve angular momentum. So there's no way to lose angular momentum by emitting light. You can only lose energy. And the configuration that allows you to do that is this kind of spinning disk. So you're more compressed, but you're still spinning, and so you conserve angular momentum. Kind of like the example with the ice skater bringing her arms in and spinning faster. You see the same disk structure when you look at protostellar disks, so stars forming. Similar also protoplanetary disks. So you see these disks happening a lot, and it's because there's this really unifying phenomenon where ordinary matter can cool down, and it can clump for that reason. Dark matter can't cool down, we don't think. In fact, I led a search for that in 2018, and I showed that actually less than 1% of dark matter has the ability to cool down. So we're able to make percent level statements about whether or not dark matter can cool down. So it's really quite impressive how much we really do know about dark matter. In spite of the fact that we haven't detected it, we know how much of it there is exactly. We know that it can't cool down. This wasn't mentioned yet, but we know it's stable. So we know if it's like similar to like, you know, some of the different nuclear isotopes that were mentioned that have a half-life. So we can actually say with some confidence, like that dark matter's half-life has to be longer than I think like hundreds of billions of years, like it can't decay. And we can say, yeah, like tons of other things about its interaction. So, you know, it's like a little bit like when Edison was inventing the light bulb, and, you know, he tried a bunch of things that didn't work, and people asked him about it as a failure. And he said, well, it wasn't a failure. I just found a bunch of ways, you know, to not make a light bulb. And the same is kind of true doing all these experiments. It's nature telling us, no, dark matter isn't doing that. It's not cooling down. It's not interacting. It's not decaying. So we have all these great handles.
People mentioned at the beginning that there are galaxies and clusters that have either lots or very little dark energy that we can detect. Well, we can't detect. Now that we're scanning so much more and of the universe and deeper back in time, can we not do something with the two populations of a lot and very little, and to do something from the differences?
Yes, that was a great question. So the question was, so we have evidence where we have some galaxies seem to have a lot of dark matter, others seem to have very, very little. You know, given that we're scanning the sky and looking at more and more of the sky, is there something that we can learn about these different galaxies? And the answer is absolutely yes. In fact, one of the upcoming observatories that I'm really excited about is called the Vera Rubin Observatory. It's named after Vera Rubin, the woman I mentioned who she was really a leader in this dark matter research. She was the one measuring the rotations of galaxies. In my opinion, she really should have been awarded a Nobel Prize for that, but unfortunately it didn't happen, and she passed away sadly a few years ago. But she has this great observatory named after her, and it's going to be taking a picture of the entire sky roughly every 3 nights. And so by doing that, it's going to allow us to look for even fainter and fainter galaxies than what we've ever seen before. It's going to allow us to look for more and more of these galaxies where, like the ones that I showed, if you blink, you miss them, right? They're very, very faint. So we're going to be able to find more and more of these guys. And so then what can we learn? There's a lot we can learn. We can learn more about the history of these galaxies. How did they form? So I gave a little bit of an analogy with baking, right? And you have the different ingredients making like different galaxies. But another thing that's important in baking and also in galaxies is the time component or the history component. If I want to make a bread, right, I have to wait for the yeast to proof my bread and to puff it up before I can put it in the oven. But for a cake, I can put it in right away, right? So the same is true of galaxies. The history of how you assemble the galaxy and how you put it together and you cook it, that also can affect things. So we're going to learn more about that process, about baking galaxies. We're going to learn more about dark matter. I showed an example where, like, you know, we were able to say, well, dark matter is not neutrinos, because if it was neutrinos, that would have erased some of the clumps of dark matter that we see, because neutrinos are going too fast. The more and more of these small dark matter clumps we can see, we can rule out you know, theories of dark matter where you would erase those clumps. So there's a lot of classes of models that would do something like that. We can learn a lot more about those theories.
You spoke about primordial black hole. Are we sure that dark matter is not a very, very tiny black hole placed everywhere in the universe?
Yeah, so I kind of zoomed past this. Yeah, so the question was, we talked about primordial black holes, and can we be sure the dark matter is not like really, really tiny black holes placed around the universe? The answer to that is black holes are not exactly stable. So depending on the mass of the black hole, it can actually evaporate and just lose kind of, and just disappear into radiation, basically. And you can put bounds on how big your black hole has to be for it to be stable, because one of the things that we talked about was that dark matter has to be stable for like 700 billion years until today, basically. So if you had black holes that were very, very small, they would just like evaporate and you wouldn't see them today. So yeah, so there are different ways to constrain primordial black holes in different mass ranges. So Katelin mentioned like gravitational lensing. So you can essentially look at the sky and look at, you know, the lensing signatures that you see, and dark matter is actually primordial black holes, and those lensing signatures will be slightly different than you know what you see. So there are different ways to place bounds on the mass scale of primordial black holes. So they have to, so we know, depending on again when we speak to I think most of the mass range for primordial black holes has been ruled out. There's still some amount of wiggle room. If you want to make it like asteroid size, I think that still works. If you want to make it super large, I think that still works. But everywhere in the middle, we have different ways to kind of say that, oh, it can't be that because it messes up observations. Yeah. That's great. Okay.
Are there any space-based detectors being developed or they exist?
Yes, so there have been one that I know of that ran for quite a while on in space, looking for dark matter interactions. There is also discussion, and people have proposed some crazy ideas about looking for building your dark matter detectors on moons of Jupiter, and people come up with all sorts of crazy ideas. And this, the main thing here is just to get further away from things that can cause backgrounds in your detector, and also maybe change the sense of scale for what things are. One of the interesting things that people do for, sorry, I forgot to repeat the question. The question was, are there space-based versions of dark matter detectors? But yeah, one of the interesting things that people are looking for and have looked for in the past is access in MeV scale. So this is mega electron volts. So this is there's kind of a gap in what we're able to observe in astronomy so far. There's quite a lot of visible, ground-based observational facilities that can look at visible light, and also, much lower in energy like radio telescopes. But there's this big gap around 1 MeV of energy, which is around the scale of nuclear physics. All these decays that I mentioned happen around the MeV scale. And this also happens to be a part where the atmosphere is very opaque. So we can't build a ground-based telescope that can look at these types of gamma rays. We have to build them in space. And there's a lot of fruitful development there, looking for, trying to map out this part of the astrophysical space in the MeV scale of things, because it could be that there are dark matter interactions or production of particles at the nuclear scale, which is what we're kind of familiar with, that could come from dark matter interaction. This is an example of indirect detection where you're looking for dark matter annihilations that produce standard model particles, or interactions from standard model particles that are in excess. But we can't make strong statements about that right now because we haven't really mapped it out as well as we have other parts of the light spectrum. Yeah.
I have a technical question.
Oh, I actually wanted to add something to that. So some of the probes that I talked about in my talk, I would argue are dark matter detectors. So the things that are measuring the cosmic microwave background, even though it's meant to measure the cosmic microwave background, we can learn a lot about dark matter from that. And so those are space-based detectors generally. Yeah, similar to what was just mentioned, like you can actually do indirect detection. So, we spoke about make it, shake it, break it, and the emphasis was on the shake it. But if you break it, so if you have dark matter that annihilates, a lot of those candidates will annihilate into things like gamma rays. So we have a lot of really great space-based telescopes looking for those kinds of signatures. One of them being the Fermi Gamma Ray Space Telescope. And one place where you might expect to see a lot of signatures of dark matter annihilating is in the galactic center, because the density there is very, very high. So if they're going to have a good conditions to promote annihilation, that would be the most obvious place to look. And tantalizingly, there actually is a huge excess. We do see the galactic center is glowing very, very bright in GeV scale gamma rays. And that is intriguing. A really big fraction of the community, we're trying to get to the bottom of this. Could it be dark matter annihilating? It looks actually, the spectrum looks a lot like dark matter annihilating into bottom quarks. So that's very, very tantalizing. But at the same time, it could just be regular astrophysics. So maybe there's a very, very faint population of pulsars that could have a similar spectrum. And people are really trying to get to the bottom of this and figure out, is it pulsars? Is it dark matter? We're gonna wait with bated breath until we get to the bottom of this. But we've had other very tantalizing signatures as well, unexpected X-ray, like spectral lines. So you see the sky glowing in particular places in X-rays, trying to explain why that could be. Could it be dark matter? Could it be some other ordinary astrophysics process that has nothing to do with dark matter? So there's a lot of hints that nature is providing. Not all those hints are going to be good hints, but you know, there's such a wealth of information, and as I presented it during my talk, we can really look at a lot of different astrophysical systems, and we can kind of view those systems as being almost a naturally occurring experiment. So we actually have so many places we can look, so much information, many of which is space-based.
Okay, let's have one last question. Yeah.
All right, so I have a technical question about the scintillation detectors and all that, because I learned that like different scintillators are better at different types of particles. So what type of scintillators are being used at all that, and how do we know they'd be effective for measuring dark matter? That's mainly for David.
Okay, this is great because my research specialty is in scintillators. So there's a few different ones that are at Snow Lab. The one that I worked extensively on is the Deep 3600 experiment, which uses liquid argon. So it's a compressed noble gas. When you compress or condense liquid argon and gas into a liquid, it has quite a high scintillation efficiency. So scintillation is the amount of light that you get out, or the light that you get out when you leave energy into a material. And that's how the details of how all that works is fairly complicated, but the upshot is that you get light out. Argon and other noble gas-based scintillators are excellent for two reasons. One is that they're transparent to their own scintillation light, so that you actually don't have any self-absorption, which happens in plastic or other organic scintillators, where you have emitted light, and then you actually, depending on the size and where things are, you reabsorb some of that. So it makes using the scintillator as a detector slightly more complicated. The other thing is that with noble gases in particular, and why a lot of dark matter detectors have used them in the past, so DEEP is just one example. There are also the dark side experiment, which also used argon. There's the Lux and LZ xenon detectors that all used liquid xenon. Argon and xenon are noble elements, and they're atomic materials, so you can make them ultra pure. So this concentration of uranium and thorium that I talked about, uranium and thorium also produce radon, and radon is a gas that can diffuse into all materials. So everywhere in the room, there's about 1 to 10 becquerel, which is decays per second in a cubic meter of air. So there's radon in the room. There's more in your basement because it comes from uranium, and Canada has got a lot of uranium. So it's something that we have to work really hard, but because argon and xenon and other materials are atomic, we can purify them very well by removing anything that's not argon, because we know that it's not part of our detector. So it makes the purification process to remove all these other types of materials very simple. There are other experiments that use different types of scintillators. So snow, for example, is not a dark matter detector, but it's full of liquid scintillator looking for neutrino interactions, as well as neutrinos double beta decay, which is a totally different physics talk. I don't know if I answered your question. So the main thing, I guess, once you produce light, you have to detect it. The detectors that they use are sensitive to individual photons. So this is traditionally has been done with a technology called a photomultiplier tube. And similar to this NEWS-G experiment I told you before, where you can turn a single electron into a billion by creating this avalanche process, the same kind of thing happens in these light detectors, where you can create the one photon that comes in, creates a single photoelectric electron. This is from the photoelectric effect, as described by Einstein quite a while ago. You create one electron and you amplify it through usually some kind of avalanche process. And this allows you to see individual photons and also count them, which is important. So the modern sensors that people use, EMTs, have been around for a long time, but silicon photomultipliers, you can really just count photons. One photon, two, and you can see the difference between 1 and 10 and 20 photons without ever fooling yourself. And you can use this to perform really accurate measurements of time and energy of what was happening in your detector. And you need both of those things to tell the difference between dark matter and everything else. So the more information you have, the better you can tell the difference between dark matter and literally everything else that can do everything.
So thank you everyone for your great questions, and let's thank our speakers one last time. So before you all go, I just want to give a little sneak peek about what's coming up next. So we have 2 public lectures left of this semester. There's one on November 7th, which is a public talk by the New Horizons mission leader, Alan Stern. New Horizons is a mission that is sent out to the outskirts of our solar system in 2015. It passed Pluto, and now it's really in the far outskirts of our solar system, exploring the unknown that is somewhat close by. On November 30th, we have a public talk by the James Webb Space Telescope outreach scientist, Natalie Willette, who will be talking to us about the new JWST data releases, which is very exciting. And another event that is not a talk, but just some fun, space fun to be had, is our Astro Trivia Night, which is a date to be determined. But the best way to keep up with all of these things is to follow us on Instagram, Facebook, and Twitter. We post about all our events. So if you'd like to keep up with us, please follow us there. Last but not least, we have to do a raffle. So we will be picking 3. There will be 3 people.